Good afternoon, ladies and gentlemen. My name is Ashook Krishnamoorthy, and it's a pleasure to introduce the session 8 here of this conference. I wanted to thank Professor Jablanovic for having me back. It's great to be back at Berkeley. Last year I was here speaking some sort of the application side, what's perhaps needed in terms of low energy, high bandwidth optical interconnects. And I'm really happy to report that it's a pleasure to introduce 4 speakers who will be talking about new technologies that they've developed recently to address this. We'll have speakers talking about sources, about detectors, communication links, integration. So I think you'll get the whole package, no pun intended, today. There are 2 large forces driving these technologies. One sort of from above, and that is the larger and larger data centers require higher and higher bandwidths and longer reaches. So that's sort of driving from top down and pulling in the technology into the marketplace. And from bottom up, we see chip I/O bandwidths exploding, and more bandwidth needed from each individual processor and switching ASIC. So that's sort of pushing out from within the chip, and we'll see and hear hopefully both perspectives on how this has shaped the technologies you'll hear about today. So without further ado, let me introduce our first speaker, Professor Ming Wu, and I've the pleasure of knowing all of the speakers today for many years. Professor Ming Wu is a Nortel Distinguished Professor of Electrical Engineering and Computer Sciences here at University of Berkeley. He's also co-director of the Berkeley Sensor and Actuator Center. He received his PhD from Berkeley, and he was with AT&T Bell Labs as well as UCLA before joining the faculty of Berkeley. He's published over 500 papers, holds 22 patents. He's an IEEE Fellow, Packard Foundation Fellow, and has received several awards. So please let us welcome Professor Ming Wu.
Thank you, Ashok, and it's a great pleasure to be here to talk about our recent thoughts on how we can approach Altojoule level photonic interconnect. And as Ashok mentioned, now more and more frequently, all the services are being aggregated in the cloud. The cloud really starts to account for a very significant portion of our energy usage or electricity usage. And what's interesting is with these mega data centers and connecting hundreds of thousands of servers, the traffic within the data center actually has exceeded that of the entire internet. And so it is interesting to look at all these different needs of communication. This is sort of a typical optical, or actually all the communication networks within a data center. This slide is from IBM. I'm sure everybody has a very similar type of slides. And here we see there are let's see, large number of servers that are at the bottom of the network here. And and then there are through various level of switches, eventually connected to the core routers, which can communicate with internet, and with closer to the servers, the data rate is lower, and starting to be 10 to 25, and now approaching 100 gigabit per second now. I'm sure Peter will talk a lot more about these communication infrastructure. So what's to noted is that almost from this top of rack switch up, all the communication is already been done optically. However, inside the rack, within the server, or certainly within the board and within the chip, electrical communication is still the dominant way of communication. And this is because electrical communication is still more energy efficient at these very short distances. If we look at the current state of the art for optical interconnect, which is roughly in this bubble here. This is defined in the communication energy versus receiver sensitivity. So it typically operates at about 1,000 to 10,000 photons per bit and consumes roughly a picojoule per bit. More advanced research prototypes are perhaps at 100 femtojoule per bit. If we look at fundamentally the receiver sensitivity, well, it takes about 17 photons per bit to reach 10 to the minus 12 bit error rate. So we might ask a question, well, can we achieve that kind of receiver sensitivity, but not by expanding more energy, but rather pushing down the energy by the same 3 orders of magnitude down to about below 100 attojoule per bit. Since we are part of this NSF E3S center, which has a long time horizon, 10 years, and we should be looking at more forward-looking research objectives rather than what's immediately needed tomorrow. So we had the luxury of looking into these more long-term solutions. To understand possible solutions, we look at the very simple link with a source and a detector with one stage amplifier and a very simple driver. It doesn't include all the signal processing electronics that follow the amplifier or precede the driver. And we look at the energy consumptions, and you can find that it's basically in the same space of communication energy versus photons per bit. You see 2 families of lines. One that's linearly proportional to the number of received photons. That's photon energy, or we can consider that as a transmitter energy. So the more photons you send, your transmitter has to work harder. However, for the receiver, it's exactly the opposite. If you have less number of photons received, you actually have to spend more energy to amplify the photons to the level it's detectable by the follow-on stages. And the sweet spot happens to be roughly when the transmit energy is equal to the receiver energy. And that minimum energy is further dependent on the capacitance of the receiver. So as you see, if we can reduce the receiver from 10 femtojoule facing the detector here down to about 100 attofarad, sorry, 10 femtofarad to 100 attofarad, we can greatly reduce the minimum energy from about 10 femtojoule per bit down to below 100 attojoules per bit. So this really points to direction how we can proceed with this optimization. That is by reducing the capacitance of the receiver. However, we look at the energy consumption from the optical sources. If we were using conventional lasers, even for a very good laser with a threshold current of only 1 microamp and bias current of 5 microamp, even operating at 10 gigabit per second, the energy consumptions of the laser already dominate everything else. So in order to reach this final potential, it is important to find an alternative source that doesn't require a DC bias. Well, we all know such a source. That's light-emitting diodes, the good old light-emitting diodes. Good old light-emitting diodes, however, are limited to a bandwidth of about 200 megahertz, limited by the spontaneous emission lifetime, which is on the order of 1 nanosecond. And this obviously cannot catch up with the need for our communication speed. And more frequently, lasers are used. This is a current driving force for all optical communication links. We know that the bandwidth of a laser can be modulated at multiple gigahertz, and their bandwidth is proportional to the bias or the square root of the photon density. So for direct modulation, if you bias the laser at a higher and higher power, you can operate it at faster and faster. However, this is by consuming more energy. Eventually, the laser speed also saturates at about 50 gigahertz or so. And so this high energy consumption is what prompted us to look at alternatives. That is by enhancing the spontaneous emission in a light-emitting diode using optical antenna. And this is a technique, obviously, all microwave engineers live and do every day. They use microwave circuits to shape how they will communicate and use antenna to efficiently guide the radiation. And if we look at the picture of an optical emitter, you can think of it as an optical dipole. And the dipole length is unfortunately much, much smaller than the wavelength. It's roughly about 0.1% of wavelength. And therefore, as a radiating element, it is not efficient. We all know that efficient antenna roughly needs to be a length of about half wavelength. And therefore, if we attach a metal optic antenna at the nanoscale, essentially, you can think of it contacting this radiating dipole so that the current can flow in the optical antenna. Through this enhancement, the emission lifetime can be greatly enhanced, roughly by a ratio of the antenna length to the dipole length. And with antenna gap of about 30 nanometers, we can achieve roughly about 100x enhancement. Now, LED is roughly 200 times slower than a laser. If we can somehow enhance their modulation speed by a factor of 200, we can actually make LED operating faster than a laser. This type of LED, it is also spatially coherent, so it doesn't have the drawbacks of traditional LED, which is very difficult to focus light into a single mode waveguide or fibers. This size of this LED is a deep subdiffraction limit, and it can be easily coupled to single mode waveguides. So within the E3S Center, a large number of us have been collaborating with each other, looking at what does it take to achieve this ultimate goal of 20 attojoule per bit at a sensitivity of 20 photons per bit. And our proposal will be using these optical antenna enhanced LEDs and in combination with a very low capacitance photodetector that was building into the first gain stage. Chris Kirali will follow me, talk about these receiver trade-offs. I will focus on these antenna-enhanced LEDs. Well, this is a subject that's of great interest to the research community, and so naturally there's quite a bit of work going on elsewhere, starting quite a while ago from HP labs to research institute at various places. And you can see also the evolution. It starts with just basically a piece of metal where light is coupled into so-called surface plasma mode, but they are not really radiating efficiently. To structures where you see optical antenna starts to emerge, therefore they radiate more effectively. However, the excitation of the optical antenna is rather inefficient. And this bottom diagram here from Stanford W.E. Murner's group have shown really good performance using dimolecule as an emitting element. There's a recent work in using this patch antenna, basically using metal cube as an antenna and colloidal quantum dots as the emitting elements, very high enhancement, and high predicted efficiency has been projected. This is work from Mickelson's group at Duke. At Berkeley, we've been looking at several generations of optical antenna LEDs. This is first generation we call Nano LED with arch dipole antennas. This is named after this shape of the antenna. It's similar to the two-arm dipole antenna, but we actually connect the two-arm with an arch. And they hug these semiconductor emitters exactly within the gap. This can be made by a self-aligned technique, and actually this arch help the antenna to couple better to the semiconductor. And you see here these typical dimensions are on the order of 30 nanometers, antenna length on the order of 500 nanometers also. And looking at this antenna, this is an optically pumped antenna. So if we excite the semiconductors by a laser pump, and we see that the emitted light is polarized only in the direction of the antenna. So in other words, when the emission is coincide with the antenna polarization, it emits readily and efficiently, whereas for photons coming out perpendicular to the antenna polarization, it is actually doesn't have much effect on the emission. The total intensity is rather low. So in the enhanced emission direction, we have observed 35 times stronger emission compared with the emitter without antenna. So this is rather encouraging. We have also performed a test on directing the radiation into a waveguide. So for all practical applications, we eventually need to couple light into an antenna, and this is how, by using a directional antenna, light can be directed into the waveguides. And I have to go a little bit faster. So I'd like to mention that CES Fortuna has successfully made the first electrical injection Nano LEDs. So we have moved from that arch dipole antenna to the slot antenna, which normally emits in both top and bottom direction. But if we enclose the top, all the light will come out from the bottom. And you can embed the active layers in the middle with PN junction, which lends itself to electrical injection. And this is the structure that he will report in next week's IEEE Photonics conference. And the results has been very encouraging. He has obtained enhancement of about 200 times compared with samples that doesn't have the optical antenna enhancement. So remember I mentioned earlier, 200x is kind of a milestone where the LEDs now would potentially run at a speed comparable or faster than semiconductor laser. Now looking forward, potentially there are even more interesting materials such as a monolayer semiconductors that could potentially even boost up the performance even more. My time is up, so I'll skip this and simply conclude that we have now demonstrate the feasibility of using optical antenna to enhance optical emission from LED to the point it can operate at the data rate of interest for short distance communications, and potentially this will pave a way to eventually realizing the Altojoule communications. Thank you.
Professor, we will go without at least one question. So, yes.
Is there a place for these antennas on the detector side?
Yes, so Chris will talk about that. You can have a matching antenna on the detector side.
Just one for me. Oh, you had yeah, please.
So this latest design that has vertical kind of output, are there any plans to sort of couple, how would you couple it to the waveguide?
This is like microwave engineering, even though it's coming out towards the bottom. If you design the optical antenna structure light, you can actually couple nearly 100% of the energy
Kind of like
into the waveguide.
Grading style, like?
Yeah, just antenna itself.
One more, I think, prerogative. So in the limit, you know, when you're, what do you see as the sort of quantum efficiency or conversion efficiency you think you'll get with these devices?
Eli's group have done a very comprehensive analysis of the antenna theory, considering all the practical limits. So I think the bottom line is 1000x enhancement at 50% efficiency is perhaps the fundamental limit for this technology. So in a way, it can have higher wall plug efficiencies than lasers.
Very good. Well, I hope you'll keep your questions for the panel.